All right, let's dive right into this explainer. Welcome to the simulation. Today, we're going to decode the pure underlying mathematical source code that literally drives the swinging, vibrating, and pulsing motions of our entire universe. From the microscopic jiggle of atoms all the way up to the grand sweeping orbits of moons, it actually all boils down to just a few elegant rules. We're going to be breaking down Chapter 15 on oscillations today, and honestly, by the time we're done here, you're going to start seeing this hidden blueprint of movement pretty much everywhere you look. So here is our roadmap for today. We'll kick things off by defining SHM, then look at the telemetry data, check out the energy engine, dive into pendulum physics, explore the circular link, and wrap it all up with real-world damping. Okay, starting with Section 1. SHM defined. So, the absolute most crucial starting point is figuring out what simple harmonic motion, or SHM, actually is. Just picture a block attached to a spring, sitting on a perfectly smooth, frictionless table. When you pull that block away from its resting center, the spring fights back, right? Well, simple harmonic motion happens when this so-called restoring force perfectly fights against an object's displacement. It is relentlessly trying to pull the object back to that center origin point. And the cool thing is, the further you pull it, the harder it pulls back. Now, to track this continuous, unbroken loop of motion, we rely on two vital metrics. First, we've got frequency. That's simply the number of complete cycles the object makes per second, which we measure in hertz. And on the flip side, we have the period. That's the exact time in seconds it takes to run one full cycle. These two are perfectly inversely related, so a higher frequency means a shorter period. You can kind of think of it as the heartbeat of our simulation.
Moving right along to Section 2, telemetry data.
Now, please don't let the calculus here intimidate you. Just take a second to notice the really elegant progression in these equations. We start off with position, which is modeled beautifully by a standard cosine wave. If you take the derivative of that position with respect to time, boom, you get velocity. And notice how that cosine shifts into a negative sine wave, with the angular frequency, omega, popping out to the front. Take just one more derivative and you get acceleration, which shifts right back into a negative cosine wave. It's this perfect interlocking loop of math. And that actually reveals the ultimate rule of our physics engine. Because the acceleration equation shifted back to a cosine wave, it is a perfect mirrored reflection of the original position equation. Basically, acceleration is always proportional to the displacement, but, and this is key, it's moving in the exact opposite direction. That little minus sign, that's the secret sauce. It guarantees the object is always being pulled back home. If you ever see an equation in this format, you instantly know for sure that you're dealing with simple harmonic motion. Which brings us to Section 3, the energy engine. I like to think of mechanical energy like a video game health bar. In a perfect, frictionless simulation, the total energy is locked in. It's perfectly constant. But inside that total, two forms of energy are dynamically trading places. You have kinetic energy, which is the energy of motion, and potential energy, which is the stored energy of position. As our object speeds up right through the center, it is entirely kinetic. But as it stretches out to its absolute limit and slows down, it becomes entirely potential. It's exactly like tossing a kid up in the air. When they reach the absolute peak of that flight, their speed momentarily drops to zero, right? An oscillator does the exact same thing at the edges of its movement. Right at that turnaround point, the kinetic energy is completely gone. It's banked entirely as potential energy, just waiting to be unleashed to pull them back down. All right, let's look at some real structures in Section 4, pendulum physics. Our engine basically renders three distinct types of pendulums. First up is the torsion pendulum. This one doesn't swing. It oscillates by the twisting of a suspension wire. Think of a CD hanging from a twisted rubber band. Second is the simple pendulum, which is just your classic idealized concentrated mass swinging on a massless string. And third is the physical pendulum. This one represents messy reality. It's a complex distributed mass swinging from an off-center pivot point, kind of like swinging a baseball bat between your fingers. But here is where it gets crazy. The telemetry for a simple pendulum shows us something super counterintuitive. Its period is determined completely by the length of the string and the gravity of the planet it happens to be on. Notice what's missing there. Mass. The mass of the bob completely cancels out of the equation, meaning a literal wrecking ball and a tiny glass marble, if put on the exact same length of string, will swing with the exact same period. How wild is that?
Let's shift gears to Section 5, circular link.
If you take uniform circular motion and look at it perfectly edge-on, The projected two-dimensional shadow of that motion is mathematically identical to simple harmonic motion. Way back in 1610, Galileo was watching Jupiter's moons, and they looked like they were moving back and forth in perfect simple harmonic motion. But obviously, they weren't on giant space springs, they were in circular orbits. That back and forth oscillation we observe is literally just the 2D projection of a 3D circle. The math for a spinning wheel and a bouncing spring, it's fundamentally the exact same code.
Finally, let's hit Section 6, Real-World Damping. So in the real world, obviously pendulums don't just swing forever. A kid on a playground swing is eventually going to come to a dead stop if you don't keep pushing them. So what exactly is draining those perfectly balanced mechanical energy bars we talked about earlier? Well, this is known as damped oscillation. Out here in reality, external forces, like air resistance or even just internal friction at a pivot point, act kind of like a virus in the source code. These forces do negative work on the system. They constantly bleed the mechanical energy out of that beautiful kinetic potential loop, dissipating it into the environment as heat. The math curves slowly flatten out until the system totally stops. Now, if you want to keep a damped system moving, you have to apply what we call forced oscillations, like repeatedly pushing that kid on the swing. And if your pushes perfectly match the swing's natural frequency, you achieve resonance, which gives you the maximum possible amplitude.
Ultimately, these mathematical blueprints govern the very matrix of our universe. From the swinging of an old grandfather clock to the invisible, vibrating atoms making up the room you're sitting in. Now that you've seen the code, you're going to notice this oscillating matrix everywhere. Every vibration, every swing, every wave of light follows these exact rules. Which kind of leads us to wonder, what other invisible math is controlling your movements right now? Thanks so much for joining me on this explainer. Keep observing the world around you, and I'll catch you next time.